where Open PHACTS is. Probably some of you have seen our mails about the new release of the API, which we're now at version 2.1. So there's information on our website about the 2.1 release, which covers the Shaw-Kemble data, which has recently been put into the system, as well as some extensions to the pathways calls. So we're certainly happy to answer questions on that in the support forum or in other means if you have any, and we'd certainly welcome your feedback on that too. But today's talk isn't so much about those new API calls, but more about how a couple of groups have been working with Open PHACTS, but also working with other data that is linked to what we have in Open PHACTS already. So it gives me great pleasure to introduce our two speakers today. Both of these speakers gave very good talks at our Vienna meeting, which was in February, and these sessions today are sort of a build on that from Vienna. So first of all, I'd like to introduce Jean-Marc Neefs, who works at Janssen R&D in Belgium, and he will be talking a little bit about the way that Janssen are using Open PHACTS in terms of bringing together their internal data with the public data that exists in Open PHACTS. And then secondly, in our talk today, we have Luca Bartek, who has been studying at the University of Strathclyde in Scotland. I think she's come to the end of her degree course this year, and also was able to spend at GSK in Stevenage working with Stefan Senger for, I think, the third year of her degree. So Luca, I think, hopefully has survived her exams, and I think, as I say, just coming to the end of her course there. And as I say, we welcome both our speakers, and I'll hand over in a minute to Jean-Marc for his presentation. As normal, if you'd like to ask any questions during the talks, please use the question feature in the webinar software. You can type your questions in there, and what we'll do is we'll go through the questions at the end of both of the talks, just for continuity. But if you've got any questions as you think of them, by all means drop them in, and we'll try and go through them at the best time as well. So gives me no further ado to hand over to Jean-Marc. I'll just make Jean-Marc presenter and welcome him to this session. And
thank you, Nick.
Thank you.
Thank you for the opportunity to present here. What I want to show is, I hope you see this. It should say ChemCubed queries, better, stronger, faster. Nick,
that looks good.
You can see that? Okay. I work at the computational chemistry department at Janssen in Beerse in Belgium. And we were inspired by Open PHACTS to provide integration of external data with internal data. A lot of attempts have been made to integrate several, even just pharmacology activity databases. And the structure of these databases prevents very large-scale integration. It's not inhibiting it, but it's a big hurdle. So what we wanted to have is something that is better, stronger, and faster. Okay. We have queries to activity databases, and they could be very simple, like search activity data for compounds like X. The current tools that we have are fairly slow, very cumbersome, and they only allow structure, substructure query options. So we want something that can also answer harder questions, like list molecules that are similar to molecule X and report their activities, or list activity data of a list of molecules or a list of targets. And even harder, we have questions about target-wide druggability, or companies that are working on some targets and diseases. And these are questions that were also listed and reported in Open PHACTS. So we were we have been collaborating in the last couple of years, and this really inspired us into trying to have a semantic solution to integrate external semantic databases with internal databases that had to be transformed in a semantic format. If you really want to answer a really very hard question like phenotypic screening, this is a paper that's now being published by Edgar Jacobi at our site and Daniela Diggles in Open PHACTS. It's just been accepted for publication, so it's not out there yet. But you see that if you even want to integrate that with pathways and with GEBI or gene ontology or diseases, you'll have to do some aggregation and some complex processing just to list the known knowns. So it's not about the $6 million man, but we need something better, stronger, and faster. Software that will search all available databases, that will search targets, pathways, that is fast, easy to maintain, that gives us access to new data and different types of data, and that has essentially no learning curve for users. Now this is pushing us into the direction of existing software, and we had to look for available software to our chemists that could implement these types of searches, and that would also provide results that are still usable in the same software. So what we learned from Open PHACTS is that we can provide semantic linking of pharmacology data and additional data. We find that we have to map entities and relations between databases. We have to transform our own internal data into something linkable, which is one of the major undertakings because our internal databases are essentially relational or text or unstructured. So instead of developing specific applications for each type, we want to transform the types in a similar format and provide one interface, provide an API, or provide direct access. And Open PHACTS actually proved to us the actual feasibility and usability and utility of semantic data. So because we could do a proof of concept of the Open PHACTS data with workflows and pipelining tools, we thought, okay, how could we transform something that runs on Steam into the same type of thing that runs on nuclear power or electricity, so that we have the same functionality, except that we have something that is 1 or 2 orders of magnitude faster. So we took on the challenge with a fairly small team, and it took the export of most of the ABCD data. This is our internal Johnson & Johnson pharmacology database into a semantic format. That was done by people in research informatics. We had to annotate our in-house targets, activities, assays, and compounds with public domain data to make them linkable. For chemistry, we needed to have a really fast molecule structure search engine and a powerful semantic data server and a user interface. And Herman van Vlijmen and Edgar Jacobi made sure we kept on track and we were moving forward. So at the moment, ChemCubed, what we have is a semantic database that is running on a semantic cloud, and it's installed on Virtuoso, and it answers Sparkle queries, which are actually semantic SQL queries, if you wish. It searches both our internal data, Campbell data from Open PHACTS, and the latest Campbell data from Campbell directly, plus ontology databases from Open PHACTS. So it also uses the Campbell target family information and gene ontology. So we found something that is better, stronger, and faster. If I'm allowed, I would share a demo, but I don't know how to do that. If Nick wants to help me, I want to share something else than the PowerPoint slide. How do I do that?
You should be able to share more than one application, Jean-Marc. So when you signed up to the sharing, was it share your screen?
No, it shared just PowerPoint.
If I might just, if I switch back to, if you stop sharing a minute, and then if you find the application you want to share, I'll give you back permission to share, if that works.
Yes.
Okay. So just let me, because I think you might need to have. If you now find the application you want to share, I'll give you back presenter privileges.
Okay. I've got that, and this is what I'm sharing.
Yeah, I can see that.
You should see something with a small molecule here.
Mm-hmm.
Well, what you see is a Janssen application, which is called 3DX. It's a chemistry-oriented application, and it has a number of plugins. And what Search Informatics did for us is develop a plugin that is linking to this semantic database. Now it searches compounds, and it searches, now also searches targets. So just as demo, you can search a compound against the available databases, in this case our own application, and it is doing now a substructure search, which was something that was, or that used to be really very slow until a couple of months ago. And now it has found 650 structures containing this funky substructure I was drawing. Now it also is able to search for that same substructure. I'll do a faster search here in Campbell and retrieve bioactivities. So at the moment now it's going to search for that substructure in ABCD and Campbell. And when it found a substructure, retrieve bioactivities in both ABCD and Campbell. Now, I'm working from home over a slow line, so the results may be coming back a bit slower. So I'm going to stop after a few hundred rows. Okay. You can also ask to have a minimum activity for potency data. So now it is going to find activity data for 840 something structures. And it's only going to report activity of potency of minus log 6 or higher. So it's retrieving, it should retrieve about 2,000 to 3,000 rows. I'm going to cancel because it's taking, no, it's finished. So now we have information on Campbell and we have activity data as well. The interesting thing is if you have an existing file, you can select the structures and look for activity for the structures you have selected, and it is going to find activity data for those. Or you can search information with full text. For instance, if you want to search for a compound and find its activities, this is now a search that was not possible to do before. So now with just 2 clicks, it found 2 structures, and it's going to ask for activity data about that compound. I've got 60 rows already. So these were search results. What you can also do now, and that's very recent, is you can search the database with gene symbols. So if you have a list, like you have CDK4, GSK3 beta, etc., as a gene symbol, and others, you can search for that information in both databases, and it will retrieve the data for those two gene symbols, and also retrieve by activities for those 2 gene symbols. So this is now a tool that is used regularly by our chemists, and it allows much faster and flexible searches across the databases. The plans for this year are to include additional databases from Open PHACTS, from vendors, and internal databases, so that we can have like a global search across or a search of all the chemistry across the databases that we can access. And that concludes my presentation.
Thanks very much for that, Jean-Marc. I'm sure that's got people thinking about questions, so I know I've got a couple that we can certainly talk about in a minute. So if you want to, just a reminder, if you want to ask questions, then by all means put them into the question part of the GoToWebinar, and we'll cover them at the end when we've heard Luca's talk. So thanks again for that, Jean-Marc, and we'll then just switch presenter. So going to hand over to Luca now. So as I mentioned at the beginning, Luca has just finished her degree at the University of Strathclyde, and was spent a year in industry working with GSK, and I'm sure she'll talk about some of that in her talk. And her talk is going to cover around the usage of Open PHACTS, but also some of the work that she did looking at the Wikipedia and Wikidata aspects of linked data. And I'll hand over to Luca to tell us a little bit more.
Hi, I hope you can see my screen right now.
Yes.
So, as Nick said, I'm finishing my degree now at Strathclyde University, and as my master's project, I did a project on the drug-related information that is on Wikipedia, and I used Open PHACTS in order to verify the data and see the quality, how good it is. So Wikipedia is a well-known resource all over the world. It's available in many languages and it's free to access, so a lot of people do access it. And the English Wikipedia only has over 10,000 drug-related pages. And it has been shown that it comes up on the first page of Google search results over 80% of the time. And even students of medicine, more than half of them tend to use it as an information source. And even though the data quality of drug information on Wikipedia has been researched in the past, that research was only done on 150 drugs, so it was a very small scale study. So that's why we were interested in doing a larger scale study. Yeah. What you can see here is a typical Wikipedia article. This is aspirin. At the top you see the title, which also serves as an identifier within Wikipedia. As you can see a URI there written in red, that's an example of what Wikipedia URIs look like. And then in the middle there's a big blob of text, which is the main content. It contains most of the information, and most of the time it is freely editable by anyone. It's just free text, really. And the interesting part is the right-hand side. You can see there's these tables called info boxes, or in the case of drugs, they're also called drug boxes, which are actually based on a template, and they contain the most important information of that drug in this case, or of whatever the page is about. So since this is structured, this is what I used to verify the drug data. The way I used was via the MediaWiki API, and this is just a quick screenshot of what it looks like right now. It has been changing recently. And so first of all, I needed a list of these drugs in order to get all the information. So I used a list call, and I specified that I need a list of pages which have a template embedded, and that template needs to be the info box drug. So this just gives you all the pages which have this drug box in them. Obviously this is not all the drug pages, but the ones without the drug box we wouldn't be interested in anyway. And then using this list of drugs, I used another call in order to retrieve all the timestamps for all the revisions of the specific page, and the revisions are just each update of the article. So even though in the GUI you can only see the latest version of the article, every single update that anyone has ever made is actually stored, and you can access it via the API. And then for the latest revision, so for the most up-to-date version, the content of section 0 was also retrieved, and section 0 is just the drug box itself. So from this drug box, the chemical properties and database IDs were extracted using just regular expressions mainly. And at the bottom you can see the list of the properties and the IDs that were retrieved. First of all, I wanted to see if it makes sense within each page. So if the data is consistent within the page without checking any external sources. So obviously that was possible to do for the chemical data. But in order to verify if this data actually is about that specific drug that is named, or to verify the IDs, you do need an external source. So that's where Open PHACTS came into the picture, because it's a reliable source, and also I was able to access it automatically, which at such a number of pages was obviously needed. Is the internal consistency. So just looking at the Wikipedia drugs without using any external source, this of how much information is actually on Wikipedia. So this is the percentage of how many times each property was defined on the page, regardless of whether it was correct or not. It just shows you how often each property is defined. So all the data was retrieved for just over 6,000 drugs. And in order to actually do this, this internal check, you obviously need a starting point. So to get that, first of all, I've taken out all large molecules and mixtures, antibodies, these sort of things. Then I've taken out the molecules which didn't have a SMILE string defined because I chose the SMILE string as the starting point for my internal consistency check. And there were a couple of instances where this SMILE string was actually perceived as invalid. So I've also taken those out. This resulted in just under 5,000 small molecules with valid. So that was the starting point. And then I checked whether the standard INCHI and standard INCHI key quoted on the Wikipedia pages actually corresponded to these SMILEs. And these were correct most of the time, 93 and 94% of the time, respectively. So taking those molecules out of these which had both the INCHI and the INCHI key correct, I've taken them, which was at this point just under 4,000 drugs. Taking those which had the molecular formula defined, 97% of these molecular formulae were also correct. And finally, taking the molecular weight and seeing whether they correspond to the molecular formula, it had slightly different results based on how much you rounded up the numbers, but at the end I ended up using the rounding up to the whole gram, and that was correct 97% of the time. So overall, 3,700 molecules were fully complete and consistent within the pages, which is 72% of all the examined small molecules. To actually verify if this information corresponds to the correct drug and also to see if the database IDs are correct, an external source was needed. So as I mentioned, that's where Open PHACTS came into the picture. Now, in order to get all this information from Open PHACTS, I needed a URI. And that was actually done in steps. So first of all, the easiest batch was that some of the identifiers.org version of the Wikipedia URIs were actually mapped to HMDB URIs. So these were simply mapped via the map URI API call of Open PHACTS, and this was successful for over 1,100 of the drugs, which left a lot of. The next step was using the concept search call of the Open PHACTS API. So using the get concept description API call and specifying the UUID to be a chemical viewed structurally, the query was just the title of the Wikipedia page because that is the generic drug name most of the time, or sometimes it's the UPAC name, but either way it should be a way to identify the molecule. So this call gives a number of results in each case, but the exact matches are annotated as seen here. So this was successful for a lot of drugs this time, over 2,600, but this still left a number of drugs which were not successfully matched, either because there was no exact match or because there was more than one exact match, and in the latter case, I matched them manually, 264 of them, because these had 2 or 3 exact matches, so the correct one needed to be chosen manually. So overall, over 4,000 of the drugs were matched between Open PHACTS and Wikipedia, which might not seem like a large number, but when you compare it to what had been done previously, which was around 150 drugs in previous research, it was a huge improvement. So from this point on, it was very trivial to retrieve the data from Open PHACTS because at this point we had the URIs, and with the use of 2 different calls, all the data could be retrieved because the map URI call gave all the necessary identifiers, and then the compound information call gave all the chemical data. And this was as what was seen before for Wikipedia. This time, this shows how many % of the time each data was found in Open PHACTS. And on the right-hand side, you can see the chemical data. is defined almost all the time, and then for the database identifier, the results are more variable. Have all the data from both data sources, we need to compare them. So for the identifiers and the standard INCHI and INCHI key, this was very easy. It was simple string matching. For the SMILES, it was slightly more complicated because you can have more than one correct SMILES for the same molecule. So both SMILES from Wikipedia and Open PHACTS are taken, and these were turned into new standard INCHIs, and these were string matched against one another. For the molecular formula, I arranged the elements in an alphabetical order because there were a couple of cases where they were in different orders, and this kind of took care of that. And then for the molecular weight, once again, I just rounded up to the whole gram. Results of the research, really, it shows how many % of the time the Wikipedia data was correct when taking Open PHACTS as a reference source. So considering how Wikipedia can be edited by anyone, I think that the results are surprisingly high, because even the lowest SMILES is over 80% correct. And even when looking into that, you can see that 64% of the cases, it was a simple case of different stereochemistry or incorrect stereochemistry. I could easily check that because, as I said, I generated INCHIs before, so just by removing the stereochemistry layer of the standard INCHI, I achieved higher matches. A couple of cases, it was seen that a lot of the properties are incorrect, even though they are fully consistent within the page, and that was because the title of the page was different from the actual drug that was described on the page. So the title of the page could be the parent drug, and then the data corresponded to salt, or the other way around. And another interesting thing in the SMILES was that when you have a methyl group coming off a carbon chain, so you see a capital C in brackets, as people were entering the information, it was sometimes auto-corrected to a copyright sign, so that's why the SMILES were seen as invalid when converting to molecules. Is to see what influences how complete and correct the information is on Wikipedia. And in order to see that, two scores were generated, which I named Complete Score and Wiki Score. So the Complete Score only takes into consideration how much information is available on the page, how many data properties are defined, regardless of whether it is correct or not. And then the Wiki Score takes into consideration both the quality and the completeness of the data, because you get 1 point for each piece of correct property and -1 point for each piece of incorrect property. And then obviously if it's not defined, that's worth 0 points. So having calculated these scores for all the drugs, you can see, for example, this chart shows the average Wiki score and complete score. So the Wiki score is in blue and the complete score is in yellow, versus the year that each article was created. And especially in the Wiki score, so that's the quality of the data, you can see an obvious decline in the quality of the data. And when you wonder why that is an even more obvious trend, because it shows the average number of revisions, so how many times the article was updated versus the year of article creation. And you can see pretty much exponential decline, because the older an article is, the more people have updated it, and therefore the more likely it is that data is actually correct. This is a chart that shows each of the over 4,000 drugs and their corresponding Wiki scores and complete scores. And this just kind of confirms what was seen before, because as you can see that the more you go to the right, so the higher number of revisions, the higher number of people updating it, you don't see any more bad quality data. You don't have any blue spots under zero. You only have high scores. So the more times the people have updated it, the more likely it is that it's correct. Whereas on the lower left-hand side, you see a lot of negative scores because most of these articles had been updated only a few times. So it was more likely that some of the data would be incorrect. Is that we now have more confidence in how accurate the drug information is on Wikipedia. And the drugs were mapped between Wikipedia and Open PHACTS in the case of 4,000 pages, which can be used for future research. And a number of issues were obviously flagged in the Wikipedia data, which is clearly useful because it can be edited by the community. So we have contributed to this community edited source. And while doing the research, there were some issues flagged up in Open PHACTS, and these were reported, and I think that by now they have been corrected. For your attention, and I need to acknowledge my supervisor at the university, Tel Tuttle, and Stefan Zenger, who's the creative mastermind behind this project, and also Biovia, who provided me with a free license to Pipeline Pilot to conduct this research. So I think that's it for me now, Nick, if you want to take back the presentation.
Great, thank you, Luca, for that talk as well. So let me just come back to, so what we'd like to do now is have a sort of some questions and discussions, and what I'm going to do is just have a look on the question box. So just bear with me whilst I pick out some of the questions that have come in both for Jean-Marc and for Luca there. So maybe perhaps let's start with some questions for Luca, since that was the more recent call. Certainly some really nice compliments in the questions as well. So in terms of the publicly available data that you've got with those 4,900 smiles, Luca, are those available at all, or is that something that you're thinking of publishing in the future?
I'm not sure I understand the question correctly. Do you mean the list of the smiles that I retrieved from Wikipedia, or?
Yes, that's right. Are you, and more importantly, maybe, are you thinking about publishing what you described as a paper, or?
Yes, we have been talking about that. It's definitely among the plans.
Okay, so that might be the point when you would share some of that sort of extra information. Okay. And a comment from Anthony, who's obviously one of the Chem Spider sort of founders. He mentions that Chem Spider can also provide the Wikipedia set as a download. So that may be another way, of people wanting to intersect with these different data sets. And
that's very useful to know. We didn't know that.
And it also, I think, it also sounds like Luc Patinet, who's at the Lausanne École as one of the sort of leaders there, I think, in the informatics group, has also done some similar analysis in this, or complementary analysis in this area. That's something that maybe we can follow up with Luc. I was at a meeting with him last week, actually.
Yes, that's great.
Perhaps just turning to some questions for Jean-Marc as well. Do you want the process that you went through to get your data, your Janssen data, into RDF format? Was that an easy task for you? What were the sort of challenges that you faced there?
Well, it's not really I who did that effort. That was an effort done by Research IT, and was mainly driven by Doug Martin in California, and also Dmitry Rasokhin at the East Coast. But I think in brief, the structure of a relational database in general, if it's done properly by relational database managers, is to normalize the data as much as possible. And by that, for the non-IT people on the call, that means that you have tables that contain as little duplicate information as possible. The reason is that normalized database then will provide little chance for error, because, for instance, if you have addresses and names and cities and countries, you only have one list of countries, one list of cities per country, one list of streets per city, one list of numbers or possible numbers per street. So you do not want to duplicate that information. That means that the database is also smaller and there's less chance for error. The problem is that your objects, let's say your person who lives at an address, is split over different tables. So if you want to find back a number of information about a person, you have to go and look through several tables and make a new view of a database. And that can be quite challenging if your database has tens or hundreds of different tables that are linked by keys between the tables. So that is really a challenge. You have to stop thinking in tables and you have to start thinking in objects. For pharmacology, that's very typical. You have to think in assays, you have to think in activity, you have to think in targets, you have to think in compounds. And all these entities have some properties. Like compounds have a molecular weight, smiles, inches, 3D structure, images maybe. Assays have reference documents, assays have activities, the activities have values, units, result types, etc. And you actually have to transform your mind from something that is table-oriented into something that is entity-oriented. Plus, you have also then to realize that the relations are not between tables by like matching keys to each other, but you have to identify the real relations between these objects. Like an assay has activities. An activity measures something about a compound and a target in a certain environment. That activity has units, and all these things have to be defined semantically. And once you've done that, you have actually a description of what's in your database, but it's not a relational database schema anymore. It's an ontology. And then you have to create your data in a semantic format. And in order to be able to link your data to something else, there have to be some properties in your entities that are also public. For instance, what we did, and it's not a big secret on how to do that, we just had to assign UniProt accession numbers and gene identifiers to our molecular targets. And then you can do a mapping to Chem, who also has that information, or you can do that link to PubChem, who also has that information. And you can ask your database vendors when you purchase a database that they should also do that in order for us to be able to link information to their data and to link their data to our information. So the trouble is moving your view of the world from a table space into an entity space. And that takes some warping.
Thanks for that, Jean-Marc. That was a really good summary. I mean, certainly that's something that we can talk more about, and I suppose we'll cover this actually in future talks in Open PHACTS, as I suppose it's probably right to say that Janssen's probably the first in the Open PHACTS community to perhaps try to do this merging between private data and the public data that's in Open PHACTS. So we certainly want to build on that experience that you mentioned there, and some of it is already featured in the Open PHACTS documents that particularly people like Egon and Alistair Gray developed as part of the project in terms of best practices of working with RDF. So I would recommend that, and we can send round the links to that if people are interested, where it talks a little bit about some of the principles that Jean-Marc mentioned. I mean, possibly.
Also, I wanted to have a small comment on what you're saying. We're not merging any information. We're just putting it together and hope it links in a way. So
sure.
We don't really try to. The only thing we do is put triples together in one Virtuoso database. So it's not really merging. The advantage also of this approach of extracting the information from existing databases is that we left existing processes and existing databases totally untouched. So the big fear of pharma IT and big IT organizations is that you would alter a production database by providing additional tables or linking fields or linking tables to other production databases. And that at some point there has to be some testing done, and at some point a production database needs to be replaced by something else. That means that dependent processes on those production databases also have to change. And this is like a real mountain of stuff that is behind this relational database. Merging processes, or really very integration processes, are really very, very tricky if you have large production databases and several of them to be merged. So we did not merge. We just said, like, could you just extract the information we need? We'll put it somewhere else. It's not going to be a production database. Everything can go on as before. We just have something else by the side, which is linking really very quickly all these different data together. And then everybody was relaxed and we could move forward with the project.
Okay, no, I think that's great insight, and I think it equally reflects, I suppose, on the approach that Open PHACTS has taken, you know, where we do have separate graphs of data, and the key to us, and maybe this is also you mentioned about some of the identifiers, that some of the challenges are around both the chemical space that you've integrated over, so trying to looking at being able to query consistently in a chemical sense, as well as, you know, managing the identifiers. And I suppose that's something that you know, Open PHACTS has done, and I imagine that you were coping with within your own triple store too. Is that right?
Yes, in that way, Open PHACTS has been an inspiration on, like, guiding us on the process of how we could do that ourselves. So as a matter of creating dictionaries of terms, creating dictionaries of, or actually one dictionary of terms for all different databases is also a way to go. It takes a little bit of thinking how you can create just one single dictionary, but it is feasible. And it's actually essential if you want to link several data together. You have to have one place where you say what entity in one place is similar or the same as an entity in another place.
Yes, definitely. So, I mean, I think given the sort of questions we've had today on that aspect, you know, that's certainly something that we could come back to. And I know you and your colleagues, Dimitri and others, were involved in this. So certainly if people have interest in that in more detail, we can, I'm sure we can cover it either as a separate call or potentially an extension of this talk. There's a couple of other questions that have come in as well. Just wanted to try and go through these. So one question to Luca, when you were mentioning about the table in Wikipedia and the potential for putting a Open PHACTS ID in there, is that something that's sort of in progress, or was that more of a suggestion?
Well, both really. It was a suggestion, and then when we were in Vienna, there were two guys from Wikidata there who are working to integrate the data in these tables between the different languages, and they were also in favor of doing that. So once that paper might come out and things get rolling much more now that I'm done with the university, that is definitely a possibility that it will actually happen.
Yes, one of them was Andra, wasn't it, Wagermeister? So I know we can definitely keep that sort of communication going. Okay.
Yeah.
So just again, just skimming through some of the other questions that came through. We've answered some of them because there were a couple on the same subject. So yes, I think it's definitely something we'll do, Lisa. We'll put you in touch with Anthony, who was at the RSC and who's now at the in the US Environmental Protection Agency, EPA. So we'll make some of those connections after this call as well.
Great, thanks.
So just as a bit of a recap as we approach the hour. So firstly, to thank Jean-Marc and Lisa for two both interesting talks, and one showing different aspects of using data both for internal linking with Open PHACTS, as well as opening up the wider perspective of open data with Lisa's talk about Wikipedia and Wikidata. And this is just a chance for us to tell you a little bit about the next session that's coming up in our webinar series. So we are running these monthly, which tends to be the last Monday of the month. So the next one is the 27th of June. And we're pleased to have David Wild on then from Data to Discovery. David is also at the informatics group, leading one of the informatics groups at Indiana University. And he's going to be talking us about, I suppose, a build on perhaps some of the themes we've heard today, but with a particular focus on phenotypic screening data and wanting to describe some of the work that he is doing in his group and with his collaborators in other groups around combining Open PHACTS data with proprietary and public data sources. So that's going to be our webinar for the 27th of June, and we're certainly looking for other people if you are interested in speaking at this webinar series. It doesn't necessarily have to be Open PHACTS related, but it should be something around, I suppose, drug discovery and linked data and the value of annotating data too. So by all means get in touch with myself, Nick Lynch, or others within Open PHACTS. And we'd like to again thank you for coming to today's talk. Our copy of it will be available shortly on SlideShare and the recording. And we'd like to thank both the speakers and those that asked questions, and hopefully we'll see you in a month's time, and wish you a good rest of the week. Have a nice Monday.
Thank you very much, Shane.
Thank you.